In this video, we will outline the basic steps for setting up a project in Ansys Rocky software. We will follow Part A of Ansys Rocky Tutorial 1, Transfer Chute, which is available at Ansys Help. Beginning by introducing the software's user interface, which is customizable. We may add, remove, reposition any window or panel available. The default view contains the menu and toolbar at the top. On the right, the workspace is where the visualization windows will be opened. The data panel and data editors are on the left, which we will use to display the project tree and the details of the selected items. At the bottom, the progress, status, and simulation log panels display information regarding the tasks and the project itself. Let's start by creating a new project. To set up any simulation, we go through the items in the data panel. The study entity covers the first step of the simulation setup. The purpose is to define any useful information for the project. We will access the data editors of the study item to enter the project information. In the physics step, the gravity, momentum, thermal, and coarse graining tabs are used to enable or disable the various models used in the solver. We will click on the momentum tab and set the rolling resistance model. The geometries step enables us to add default geometries, such as conveyors or surfaces, or to import our own custom geometries, walls or surfaces. Here we will import the 6 STL files, which are available for download at Ansys Help. In the dialog displayed, we'll select millimeters as the import unit. Ansys Rocky always saves the project in two parts. Project name.rocky is the project file, which includes the simulation setup values, and project name.rocky.files is the project folder, which contains all the generated configurations, logs, and calculated time steps. To share a project, it is very important to always send both parts. To visualize the freshly imported geometries, click and hold the geometries entity in the data tree and drop it on top of the workspace. And here's a tip. Use the mouse and keyboard shortcuts to modify the view. Left mouse click rotates the view. Right mouse click pans the view, and the scroll wheel can be used to zoom in and out. For keyboard shortcuts, R fits the view within the window, and X, Y, and Z can be used to align the view to the axis. Next, a surface must be defined to use it later as an inlet to release particles inside the domain. By right-clicking on Geometries and then clicking on Create Rectangular Surface, a new entry will be added under Geometries. Here we will set the values for name, center coordinates, length, width, angle, and vector. Enable the transparency parameter on the skirt to improve the visualization of the surface that has been automatically placed as a red box in the 3D view after its creation. A 3D view window can be changed by right-clicking anywhere in the background outside the geometries parts. Here's an example of a background change. The color, transparency, and visibility of each part of the geometries can be changed in the Colorings tab. Here we will multi-select all 6 of the imported walls, and in the Colorings tab we will enable the transparency checkbox. Movements can be added using motion frames, in which every frame can have multiple motions defined. In order to set up a new motion, we will set 2 separate translation movements. Both movements will use the global option. This means the particles in contact with the geometry will have the prescribed velocity, but the geometry itself will not move. Once both the motion frames have been created, we will assign them to their respective geometries. The materials step allows us to define the density, Young's modulus, and other values we want assigned to the particles, belts, geometries, and fluids for SPH simulations. For this tutorial, default values for the 3 default solid materials will be used. Once all the materials have been defined, they must be assigned to the walls and particles. Because 3 of our imported walls are actually conveyor belts, we want to be sure to change the materials for those components. materials interactions define adhesion and other properties for the interaction of the materials. In this simulation, we have 3 solid materials. For every pair of materials in contact, a set of material interaction properties must be defined. Here we have listed the parameters that will be changed when default particles is paired with default particles, with default boundaries, and with default belt. The particle step is where we define particle shapes, sizes, and other attributes. By right-clicking on particles, we will create a new one. We will define the size in the Size subtab and the rolling resistance in the Movement subtab. By clicking on View, a new Particles Details window appears, showing the transparent particle, its geometric center, the yellow dot, and its center of mass, the blue dot. The Inlets and Outlets step allows us to define how particles and fluid enter and exit the simulation. By right-clicking on the Inlets and Outlets entity in the Data panel, we will create a particle inlet. We will select the inlet surface as the entry point and select the particle created in the drop-down list. Then, we'll set the mass flow rate and the stop time. Prior to processing the simulation, we can use the Inlets and Outlets Info tab to review how many particles Ansys Rocky expects to simulate. When viewed from an individual inlet, we can see an estimate for only that entity's particle contribution. The Solver step is where we define processing time and stability details, and finally, start processing the simulation. Here we will set the simulation duration to 13 seconds. In the General subtab, we will select the simulation target and number of processes. For this tutorial, CPU will be faster due to the low particle count. Then, we will click on the Start button to begin processing. Once we click Start, the simulation summary window will appear. It shows the geometry bounds, enabled models, wear, breakage, non-round particles, number of particles and triangles, and the calculated time step duration. This window will disappear on its own. Then processing begins. Through a 3D view window, particle states can be viewed in real time. Ansys Rocky was successfully used to set up and process a transfer chute simulation. Make sure to check Part B, where we will introduce various methods for analyzing a simulation after it has been ran.